This is Image Super Resolution Reconstruction Online System. And this is Group 6. Our group member is Chen Zihao, Pu Maer, Liu Haoran, and Sen Jinyu. And for the first part, project description and objectives. With the rapid development of science and technology, pictures play an increasingly important role in people's daily life and production. For example, in the daily life, we will share a lot of emojis and pictures on cell phone. And when the receiver taps on the preview image, the reconstruction of low-resolution images is needed at this time. Also, in the production field, ships at sea need to transmit high-definition pictures to office building online, and the pictures need to be recompressed during the transmitting process, and then reconstructed into high-resolution pictures at the communication terminal. Usually, the most direct way to improve image resolution is to improve the optical hardware in the acquisition system, but the manufacturing process to improve the optical hardware seems too costly. Therefore, we designed a super resolution reconstruction system that helps to recover a given resolution, low resolution image into a corresponding high resolution image, and in 2 times, 4 times, or 4 times plus size of the original size. The system consists of 2 parts, front end and back end. Front end will provide a smooth UI experience in the form of web page, and the back end will be responsible for storing and manipulating data. Users can log in and register on the website, and then upload pictures of the appropriate site. Through the algorithm PRS-PM, SRGAN, and VGG19 on the backend, the system will finally return high-resolution images for users to download.
Part 2 is related to system model explanation. In this part, we have 4 topics totally. The first one is data required and available. In this project, the models will train on a large and open source dataset, COCO 2014, which consists of a training set and a validation set with 123,285 images for the training process in total. For the testing process, 3 open source datasets are applied, Set5, Set14, and BSD100, which together provide 119 test images. These test sets are practical and typical image sets commonly used for super resolution model performance testing. In this domain knowledge part, I will illustrate 2 different model structures, SRSNet and SRGAN. As we can see in this figure, SRSNet model uses multiple diff residual modules for image feature extraction, and multiple skip connection chains are used to connect the inputs to the network outputs. This structure ensures the stability of the entire network. Due to the use of a deep model, the image features can be extracted more effectively than a shallow model. SRSNet uses 16 residual modules. Another important deep network structure in this model is subpixel convolution. Subpixel convolution is a clever method of image and feature map enlargement, also known as pixel shuffle. The main inspiration for GAN comes from the idea of gaming in game theory, which is applied to deep learning by constructing 2 deep learning models, generator and discriminator. The generator model uses the exact same structure as SRSNet, except that the truncated VGG19 model is used to compute the loss function. Note here that the truncated VGG19 model is only used to compute the image features and is not added as a submodule behind the generator itself. Since the generator part of the SRGAN algorithm used the exact same structure as the SRSNet model, we could use the previously trained SRSNet model to initialize the generator directly during training to speed up the convergence of the whole algorithm. The discriminator network is constructed by several convolution blocks. The figure above shows the results of super-resolution reconstruction at different epochs. Each image has 3 columns. The first column is the low-resolution image. The second column indicates the super-resolution images constructed by the current model, and the third column are the actual real-world images. As the number of iterations increased, the super-resolution reconstruction becomes more and more effective. And by the last epoch, the image has significantly weakened the effect of blocky noise, and the images are smoother and clearer. As we can see from the below graph, at the end of training, the generated super-resolution images are already very close to the original graph compared to the SRSNet. Its generated images are more in line with the real thing effect. In the model ensemble part, we trained 5 basic SRSNet models respectively in order to be used as the generators of SR-GAN models. The first one is the original SRSNet model. In the second one, we added a dropout layer behind first convolution blocks, and the dropout rate equals to 0.3. Then in the third one, 3 dropout layers were added, and the rate became 0.2. The last 2 is shown in this figure respectively. At first, we use a initial weights list for the models. To calculate the evaluation matrix, a truncated VGG19 network structure was used to construct feature maps to calculate the mean square error. With the calculated results, we could obtain a relatively optimal weight for the model ensemble. Then we are able to get a final result.
In the part 3 section, we will give a brief overview of the system design. The front-end interactive pages, the Django web service, modes and database together make up our image super resolution system, which allowed our system to provide a better experience to our users. The front-end interactive pages use a technology stack of HTML, CSS, and JavaScript. The styling and element design of the pages is implemented by HTML and CSS. JavaScript is used to perform dynamic page elements and to communicate with the web server. The backend web framework uses the Django, which provides many web-related components for simple and fast web development. Our system is responsible for receiving requests from users to the backends via front-end pages, distributing these requests to different views via routing, and returning the result to the front-end interactive pages for display. The database used for this system is the SQLite3 database, which is a very lightweight database that allows for efficient data storage. The database of this system mainly works with the backend to implement functions such as user login and registration. Modes of image super resolution plays a very critical role in our system. The mode is deployed on the backend of the system. It receives the images uploaded by the users, pre-processes them, and finally returns the processed result to the web server. Our system can be divided into 3 main use cases, and we will explain the data flows and techniques according to these use cases. In the login use case, the front end sends the user's input to the backend as an HTTP post request. The corresponding functions on the backend compares the user's input with the user's data table in the database, performs user verification, and returns the corresponding result to the front end. In the registration use case, the front end sends user's input to the backend as an HTTP post request, and the corresponding function on the backend accesses the database and compares the existing user data table. When the user's input matches the criteria, the function writes the new user's data in the user data table. When a user processes an image, the front-end page sends the user's uploaded image and then selected mode information to the backend as an HTTP POST request, and the view function responds the request and calls the corresponding image super resolution mode to process the image. When the processing is completed, the backend sends the processed image to the front end for the users to download. Generally speaking, the server provides the download function for users by storing the file on the server side and then sending the file to the user via the file response method. But the images contain lots of user privacy, and we believe that no user would want to have their photos saved on the server side, so it's vital to protect the user's privacy. In this system, we use the following methods to achieve the user's privacy protection. First, the system calls the IO bytes IO method to open up a section of byte stream space in the memory. Then the processed data is encoded using the base64 method, and the encoding image is stored in the byte stream space. Finally, the image is rendered to the front end using the Django's render method and downloaded using HTML8 tag.
We will then present a demo of this system. Firstly, upon entering the system, the first page we will see is the home page. This page contains a navigation bar at the top, a file selection area in the middle of the page, and an upload button. This page provides the main function designed in the UI part. For example, the image selection, upload, and download. The top navigation bar can take us to the About page, which contains information about our team members and a brief description of the project. Back on the home page, we can also find the Login and Sign Up button on the navigation bar, which will take our users to the corresponding forms to perform the corresponding login or sign up actions. Now that we are not logging yet, I suggest you can see that we can only select the default 2-time size in the SR level selection field. All other options are disabled. We can either select a local file by clicking on the Choose File button directly, or we can drag the file we want to process directly into this area. Once selected, click the Upload button and wait patiently for the backend model to process. Once the processing is complete, a thumbnail of the image will appear in the middle box, and, following the prompt text, we click on the image to download it. Once the download is complete, you can see the twice upscale image processed by our model. To better show the model's performance, we register a new account for this demo here. After registering with a new, unregistered username and password, you can see that the SR level selection area is now fully open. The user can choose according to their need, considering the trade-off between image processing time and processing quality. We start with the middle 4 times. Once the model has been processed in the backend and download, you can see the 4-time upscaling image processed by our model. Let's then try the 4-time plus option with the same image. This option will give us a better image processing result with the same 4-time upscaling, but the disadvantage is that it will take relatively longer. We compare the finished image visually. From left to right, the original image, the super resolution image with the 2-time SR level option, the super resolution image with the 4-time SR level option, and the super resolution image with the 4-time plus SR level option.
As for the part 5, project concluding, The advantage of the system is that we use SR-GAN algorithm to reconstruct low-resolution images. And then, to improve the performance of SR-GAN, we propose to use model example by adding dropout layers to increase the diversity and randomness of models. And also, truncated VGG19 network structure was used to determine the weights of each SR-GAN model. And by calculating mean square error between HR image and SR image after feature mask extraction, finally we got a relatively optimal weights list for model example. However, there are also some limitations in this system. First, it is difficult to make huge improvements by modifying the architecture of the model, like adding or reducing some residual network blocks or convolution blocks, because of the large computing resources. And second, the system has a single function. So for the future work, in the future we can add the function of blurred video repair to make the system function more diversified. That's all. Thank you.